So as we jump into Module 8 here, we're going to be looking at the topic of failure theories. Now previously in this course here, we looked at the determination of loads with stresses and deflections caused by those loads and with the ability of representative materials to resist the standard test loads. Now as we continue on now and we begin this new chapter right here, the topic of failure theories, we're going to be looking and concerned with predicting the capability of materials to withstand infinite combination of non-standards loads to which they are subjected as fabricated machine and structural components. Now, the selection of appropriate safety factors is going to be very important. This is going to be to provide the required safety and reliability. Now, with earlier chapters, we're still going to be concerned primarily with static loads as we're looking at these. So within this module, what we want to look at here is different types of failure, talk a little bit about fracture mechanics, then get into some stress and fracture theories, discuss reliability, and then get into safety factors as well. Now, relating back to your textbook here, this is Chapter 6 that we're dealing with here, and we're breaking this into two sections, Chapter 6, Sections 1 through 7, and then Chapter 6, Sections 8 through 13 in your textbook. So as we begin Module 8.1, we're looking at the topic of failure theories. So within this, we have a couple different objectives. We're going over our types of failure, talking about the failure theory, looking at Moore's circle, discussing our maximum stress theory, and also looking at some different testing machines. So within this module here, we're going to go over some of the governing theories, talk about some of the key equations, look at some practical applications, and then go through some problem solving. So relating to our textbook, this is going to be covering Chapter 6 with the topic of failure theories. So let's take a look at these different types of failures. So within this, as we're looking at these different types of failures, we want to ask ourselves a few different questions. The main question we want to ask ourselves is what in a design is going to constitute a failure? So what are we considering as failure for the design that we're working on? Now, within that there, we can also ask ourselves some sub-questions here of what are the mechanical outcomes, what can affect these mechanical outcomes, and then also, are there some non-mechanical failures? What might these non-mechanical failures be? So first, let's take a look and define what are mechanical failure outcomes right here. So what are some of these mechanical failure outcomes? Well, some of these could include fracture. It could be yield or permanent deformation, excessive deformation, or buckling. So these are all types of mechanical failure outcomes right there. So if we think about these, let's just go to a simple case. We're thinking about a tensile test where we got a dog bone specimen that we're pulling in tension right there. Well, these are all the mechanical failure outcomes of that part right there, our dog bone specimen right there. So we could have fracture. We could see that, we could observe that, we could look at our stress strain curves to determine the fracture there. We could also have yield or permanent deformation. So again, that's something we could look at our data from that individual part to determine, okay, did it go past the yield point there? Do we see that permanent deformation? Or when we unload it, does it return to its shape, its original size and shape? So that right there could be our determination of failure right there. If we load this part, and it exceeds, it yields, and it has permanent deformation, when we unload it, it doesn't return to that same size and shape, then that could be a failure for us, because maybe it's a part that needs to be loaded and unloaded, loaded and unloaded multiple times as its function within the whole system or the whole product right there, so that if there is yielding occurring, we're considering that to be a failure for this individual design right there. Other designs, maybe that yield is not important, is not considered a failure right here. But this is one right here, what we're talking about now for mechanical failure outcomes right there, where if you do have that permanent deformation, that could be considered a failure right there. Another one could be excessive deformation. Maybe if you go past a certain point, there may be a percentage right there that if it deforms past a certain point right there, that's going to be considered a mechanical failure right there. And then buckling also is another one right there, and that's a pretty straightforward one. If you see buckling going on, you can even observe that occurring in most cases right there, that would be another example here of a mechanical failure outcome. So looking at this picture right here, one thing that we do want to think about with these mechanical failure outcomes right here is not only how it affects the individual part, but how it affects the system as a whole. So even if one part on something, a plane right here, fails, how does that affect everything else within that system right there? Does that cause other things to fail and a whole catastrophic failure, or does that just one part fail and there's redundancy in the system and it's not as crucial? So those are all types of things that we need to consider within this design process. So continuing on with our topic of these different types of failure right here, let's take a look at mechanical failure outcomes and what they're affected by right here. So they can be affected by crack propagation, fatigue, creep, surface damage, surface wear, and environmental conditions. And within the environmental conditions, we're taking a look at things like corrosion and chemical effects, thermal effects, light, radiation effects, and biological effects. So again, relating this back to our design process, how do we design for these type of things? So we can think of each of these, think of how they occur for our individual product, part, or system right here, and think about how we could make things, how we could adapt things, change things in order to reduce these right here. So if we're talking about, let's just say, surface damage right here. Now this is something we want to consider where if a part's being used over and over and over again, or if we're talking about that airplane again right there, you've got wind and you've got surface damage from particles in the air, from rain, from dirt, dust, all those types of things, and you're having that surface damage right there. Well, what could we do to protect that surface? Is there a coating that we could put on and apply? Is there a type of cleaning system that we can use in order to protect it a little bit better? Is there things that can be replaced? Is there a skin that we could use over the outside stuff? Is there a different material that we could be using that's not going to be damaged as quickly? So all of those are factors that we need to consider when we're talking about this. So this is why we need to stop and think. If we're talking about this topic right here of mechanical failure outcomes and what they're affected by, well, if we understand what they're affected by, how can we address each one of those issues right there with, again, a design criteria, a different type of material, another creative thought right there, like we're saying with these skins and things like that. How can we go through and modify these to reduce that? And I know we've talked a lot about how people are intended to use this product right here and how sometimes they use it out of the intended use, and that's definitely something we need to design for. But the thing that we also really need to design for as well are these environmental factors right here. And a lot of these are going to be out of our control. Now we can take a look and say, well, this is typically going to be used in this climate right here, so those, thermal effects are going to be great importance because we're going to be in a warmer climate. Or maybe we're going to have this in Alaska and thermal effects up there because it's going to be really cold. So you might have extreme and cold due to where the product is going to be used primarily. We got to think of, well, maybe somebody else is going to use it elsewhere outside of that type of environment right there. So you need to have a range that this can, or at least understand the range of temperatures that could affect this right here. Same type of things right here, light and radiation effects are something that are environmental that we have little control over. Some of these right there. Is it going to be out in the sun a lot? Is it going to be fading a lot? And is that fading of it right there going to deteriorate anything, or is it just aesthetic? And then we got to think about the environment right here. Is it a corrosive environment? Are we going to be near the ocean? Is there going to be salt that could affect it? Maybe this is not even just the ocean, but maybe this is in the Northeast where we have brine that we're using there, and it's part of a car right there. And all of a sudden you're going to have that salt water right there coming up on that part right there, or that system right there. And is that going to be an effect right there? So these are all things that we got to consider that may be out of our control, but we need to consider them within the design process, and they could lead to these different types of failure, particularly here the mechanical failure outcomes. So these are things that can affect that mechanical failure. So within the design process, there are some other things that we're going to refer to here as non-mechanical failures. So what do these things include? Well, these could things like marketing. So it doesn't achieve the market share, it doesn't achieve the projected profit margin. So these are all things we think about, again, at the beginning. When we talked about this design process, we said we want to see what exists out in the market already, and is there a demand for it? This may be something that you are very passionate about, and you think it's a great product, and you think that everybody's going to like it, but have you done your market research? Have you really tested it out there and see, well, will this actually sell? Will this actually be able to be sold for the price it's going to cost me to make it, to manufacture it, the raw materials, all of that right there? So all of that becomes very important, and this could be a failure of your whole part, even though it mechanically is sound and works great. If it fails in the market side of things, it still doesn't go anywhere. So that's something that we do very much need to consider from the beginning of this. And it's also good, I think, to work, especially within this course here, how we're working in a group together so we can get feedback from other people. Because sometimes we're blinded by how much we want something, how great we think it's going to be for ourselves personally. But the question is, from there, do other people feel the same way? And do they feel the same way enough so to pay what it's going to cost for us to make that projected profit margin off of it right there? And this really comes into play too when you're talking about getting investors, doing pitches and things of that nature, where you need to lay this stuff out. So this, I think, is a necessary evil when we're talking about the design project right there, is even if you do have your own money, your own funding, your own investment already lined up, maybe doing out your pitch to yourself even, or your pitch to some friends and colleagues to get some feedback on this, to really decide, is there a viable market for this product? And again, this is very hard for us to get out of our own box, our own comfort zone, and get other people's opinions and take that as constructive criticism and say, well, it's kind of an interesting idea, but there's no way I'd pay X amount of dollars for this, or, well, it kind of already exists out there. I don't really see a need for any new version of this right now. The existing one's fine. I don't think you're going to make the extra money. All these different types of questions come into play when we're talking about marketing. So that's one type of our non-mechanical failure right there, is our marketing. The next thing I want to talk about with non-mechanical failures here is technology becomes dated. And this can happen a couple of different ways. One of the biggest ways that I've seen personally in a lot of the projects and stuff that I've done is just the amount of time that it takes to actually get something designed, developed, to market, or to patent, or whatever it is. Sometimes this takes years. And again, this kind of comes back to a little bit with that investment and having the capital, money, and resources up front to make it move quickly. Because if you don't move quick enough, especially some of this new emerging technology, it's going to be outdated before you're even ready to take it to market. And it could just be an individual component within there. Maybe you got a computer in there and it has a certain processor, and all of a sudden, by the time you get developed, there's a faster processor ready to go for a cheaper amount of money. Things like that. Or it could just be the technology in general of what you're actually building. That device you want to use is going to be outdated before you even take it to market. And I think a good example of that is Google Glass. And there's a couple reasons why that really didn't take off. But the amount of time that they're hyping it and hyping it and hyping it, it was such a small window that people thought something like that would be interesting and viable and usable, and there'd be a market for it. And by the time it actually kind of got to the point where it would become a product, it was kind of obsolete and people had moved on and said, yeah, I'm really not going to be wearing anything like that. So it could be trendy. So trends are something to be cautious of too. So with the technology becoming dated, that's how technology can become dated. If something is very popular, but for a very brief period of time, that might not be a good area to get into unless you can quickly get in there, capitalize on it before it crashes, before it's not trendy anymore, and then get out. So those are also things to consider right there when we're talking about non-mechanical failures right here, is the technology becoming dated. So again, speaking of timing and how long it takes within the design process there, another thing we want to consider here are the materials or the processing and availability of the costs changing. So as you're starting it, maybe you're starting your pitch, you're working with your client, you're coming up with your cost analysis for everything, you're talking about all these different materials and the processes that are available and what those are going to cost. You write that all up in the grant proposal, you write that up to your client proposal, whatever it might be, or it's just in your budget for your own personal one right there. Well, as time goes on, maybe that specific product or that specific material you're going to use is now obsolete. So if that's obsolete, now you've got to pick a whole new product, redo the design on it, redo the cost analysis on it, and then go back from there. Or you might find that just over time, with this inflation, things are increasing in price. And it might be a combination of the two. Maybe the supply is dwindling on something, or the demand is really high, so it's harder to get that certain product, so all of a sudden the costs go up for that there. So these are all things to consider, again, as another non-mechanical failure, because if those change, if one, the material you wanted to use is kind of the only material you could use for that, then all of a sudden it's a non-mechanical failure because you can't get that material anymore. Or if the cost goes up so much either because of inflation or because of the availability of it, and it makes it no longer marketable, profitable, and you lose money for this right here, then it's a failure again right there due to that. So this is another thing to consider right here when you're thinking about your material selection is, how long has that material been around? Take a look at the price range over time. How has that pricing changed over time? And then take a look at that and say, is this something that's going to stick around? Am I going to have the time? If it's going to take me 2 years to develop this, do I have a good inkling that this material is still going to be around? And do I have a good idea of how the price is going to change with that? Now, some of the stuff you can't really predict, but the more research, the more background you look into this, the better idea you're going to have with something like that. So now the next topic for non-mechanical failures I want to look at here is safety and liability. So this is something also that's a very important topic to discuss and to consider with this here. That as design engineers, we often don't necessarily think about that. And sometimes it's great with a bigger corporation or company, you can have a department who that's what they think about and that's what they're concentrating on right there. So this is something I'd say the first thing you really want to consider, especially if it's your own company, is to make sure you have a good insurance policy. If you're part of another company, a bigger company, hopefully they have their own insurance policy set in place for that right there. But if we're talking about this here, we're developing a product and we're thinking about safety of it. Is this going to hurt somebody? Are they going to use it outside of its intended use and they hurt themselves and all of a sudden they decide to sue you and you're liable? There's a failure right there, not just necessarily of that product itself, but maybe of you and your company as a whole right there. So how do we deal with those type of non-mechanical failures right there? So that's another thing within this whole topic right here of how do we deal with each of these. We're talking about what each of these are, how do we deal with each of these? How do we prevent these type of non-mechanical failures right there? So this right here with safety and liability, that's where we design with a safety factor right there. So that's a big thing that we want to discuss right there, is how do we design with a safety factor right there to take these in. One, people using it outside of its intended use, and two, to prevent us from being liable for something right there. So that are the big things we want to consider within that design process right there for safety and liability that are non-mechanical failures. And the last topic we're going to take a look at here for non-mechanical failures are environmental impact right here. So this again could be a lot of different things. Well, it's in use, the environmental impact there. You know, maybe the carbon emission or the byproduct that's being put out. Is it going to be harmful to the environment? This is something that could be, again, a non-mechanical failure because it's harming the environment, and then it gets pulled. EPA, FDA, whoever it is, comes in and says, no, 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 you can't have that. You didn't follow all of that criteria that we talked about previously there, looking at all these standards and regulations that we need to follow. If it isn't designed for that, and all of a sudden there are these adverse environmental impacts, that right there could cause a non-mechanical failure right there, and the whole product, the whole part, whatever it is, could be yanked right out right there because of those environmental impacts. So as we mentioned earlier, a lot of the loading we're dealing with within this modular here and within this course right here for that matter is going to be dealing with our static loading right there. So with our static loading, let's take a look at some of the static failure theories. Now, a great resource for the static failure theories right here is our typical stress strain curve. We can get a lot of information from the stress strain curve right here. Now, whether this is something that's given to you from the manufacturer, and you have this information that you can take a look at for these different types of materials, or if this is something that's you've developed from testing. So maybe it's a product, or just a sample, a dog bone specimen right there that you're looking at right there, and you want to take a look at the mechanical properties of it right there. Well, the stress strain curve is a great way to do that. So a lot of times we're doing a typical tensile test right there. We get our raw data and that force displacement mode right there. So with that there, with our dimensions, we can go from there and create our stress strain curve with our basic equations right there for stress and strain. We can use that information from dimensions, our force, and our displacement as well. From that raw data, we come up with a curve that looks like this. And in particular here, let's take a look at the material and like, is it a brittle or is it a ductile material? And within that there's a couple different options there. So if we know this material is either brittle or ductile right there, that could help us in our design process decide like, yeah, this material is going to be a little bit too brittle, let's take a look at a different one, or this one's going to be way too rubbery for what we need it for. You know, we need to go with something that's a little bit more towards the brittle side of that right there. So we look at this right here, and if we're talking about our stress strain curve related to this right here, if we're talking about brittle material, we can see a very, very steep curve coming up right here for that type of brittle material like that right there. So with this right here, what we know from that there is it's going to be a very little bit of strain for quite a lot of stress. We're going to see a lot of stress on this object right there and not much strain right there. And it's going to be a real brittle, quick failure right there once we get up to that loading right there. It's not going to change. It's not going to actually deform or strain very much right there. So the other type right here, let's see ductile. Now we have a little bit more of a curve right here heading in towards the strain region right there. So not quite as much stress right here, but we're seeing a lot more strain going on. Then we also have the case right here. We can see the shape right here. Now we can see we have necking occurring going on within this curve right here for this ductile material right there with necking. And then we have this elastomeric rubbery material right here, which we can see follows a curve like this on our stress strain curve right there. So a lot of information that we can determine that we do know when we're asking ourselves, what do we know, right from our stress strain curve for these different types of materials right here when we're talking about the ductility. Now I want to take a minute here and do a little bit of review of Moore's circle for plane stress right here. So this relates back to your Mechanics of Materials course, your ME14 course right here. So what we want to take a look at here is actual Moore's circle. So with the physical significance of Moore's circle for a plane stress that's established. So we have one of these that is established and may be applied with a simple geometric considerations. So critical values are estimated graphically or calculated right here. So we can estimate these graphically or we can calculate them there. So Moore's circle gives us this estimate, this visual graphical estimate right here in order to get these values right there. So if we have a known state of stress right here, plane stress right here, whether it's our sigma x, our sigma y, or our tau xy, we can plot the points x and y and construct a circle centered right here at this value C there. So we have this relationship here that our sigma average, our average stress right here, is equal to our sigma x plus our sigma y over 2. And we can go back up here. We can see this is our sigma y. This is our sigma x right there. So we can see these for our element right there. So it's our sigma x and our sigma y right there. And our radius right here, our R value right here, is equal to the square root of that sigma x minus sigma y all over 2 squared, plus our shear stress, our tau xy here squared. So we can come down here, our tau xy on our graph. This is our tau xy on our graph right there. Now we can then obtain our principal stresses at A and B. So we have these at the two outer sides of the circle right there. There's our A, there's our B, and we can see if we go right here from our 0 point right here to our origin right here, out to A, this is our sigma max, and then out to B, this is our sigma min right here. And then we have this relationship that we can see here, that our sigma max and sigma min is going to be our sigma average right here, that we calculated from this right here, plus or minus our R value, which is obtained from this expression right here. Now let's take a look at a simplified case here for Moore's circle right here for plane stress, and let's just take a look at Moore's circle for eccentric axial loading right here. So within this one right here, what we have here is we have just this axial loading right here. There's our P, and there's our P prime right there for this element right here. Now we can see what we have from this here is we just have our sigma x going along our x-axis right here. So we have our coordinate system drawn out, our y going up, and our x going along this direction here. So we can have our sigma x going along our x direction right there. And while what we can see here, this is our corresponding right here, our Moore's circle right here in the center. So for the simplified case, you can see right here, there's our y, there's our x, or corresponding to our previous slide, our a and our b right there. So we know this is going to be our max sigma right there, our max stress out right here. And now we can see on our tau axis right here, our y-axis is our shear right there. So if we go up right here, this is going to be our D right there for our max shear at that point right there. Now our governing equations, again, we recall that our stress in the x direction right here, normal stress in the x direction, our sigma x is equal to our load divided by that area right there. And our y direction right here, our sigma y is just going to be equal to our tau xy, which is equal to 0 right there, because we just have this axial load right there and right there like this. So now we can see for our sigma prime right here at 45 degrees right there, then we can see that our R is equal to our tau max, which is equal to our P over 2A right there. This is the element showing our maximum shearing stress right there at 45 degrees. Now we can see this is equal to R, so if we go back to our part B right here for Moore's circle, R is the radius of that circle right there. So we can see that is the case. If we went straight up here to D, where we can see that is our max shear right there on our y-axis right there. That is that R value right there, which is our tau max right there. So if we're to take a look at a simple tension test right here, this would be that case right there of a pure axial load right there on our element right there. So you can see our load, which would be our P and our P prime from our previous slide right there for a pure tension test right there. So it would tell us in our problem statement over here for this simple little diagram we have to apply a pure elongation to a dog bone specimen right there. So that's what we're looking at right here. And we want to draw our Moore's circle for our failure at, and that give us our failure at 100 KSI. So we know that this point out here on our sigma axis is going to be 100 KSI. It starts from 0 right there. So from that right there, that we know that our R value is going to be our diameter over 2, and our diameter right here, if it goes from 0 to 100, our diameter of this is 100. So therefore our radius right there, so if we're going from right here to our center right here, up to here to our tau max, that would make our tau max 50. This is a quick way that we can get that tau max right there from our Moore's circle. We also had the way to calculate that. We saw that our sigma was equal to P over A, but our tau max was equal to P over 2A. So that would make that, again, a double check right there, that would be 50, because that's going to be half 100, because it's over 2A to get our max shear, as compared to our normal stress right here, max, is just going to be P over A. Now, one thing I just want to take a little aside and mention here is there are some great programs online that you can actually draw out your Moore's circle for some specific examples right here. So again, if you know one of these, your normal stress in your action, normal stress in your Y, or your shear stress on a face right there, you can plug these in, you can put in your angle of rotation, and it's going to give you a visual of your Moore's circle right here. And it's really nice, this color coordinate right here. You can see your original stress, your principal stresses right there, transform stresses and extreme shear stresses, all drawn out on a graph for you right there. And they also give you the results as well. And I think with a membership, you can export them to certain different formats. So this is just a great resource right there. If you want to double check your work, like we said, you can do it by the calculated way, or we can look at Moore's circle. If you want a good visual right there to get that estimate and double check your work right there, this is a great option to have. And there's many sites like this. This is the site right here for this one. Now this is something also that you can draw out in MATLAB. So MATLAB is another great resource as well for drawing these out. And there's a lot of, if you go to MathWorks, there's a lot of good resources there for some script files that are free down on their Exchange network right there for these different types of Moore's circles representations within the MATLAB environment. So let's take a look at the Moore circle here for another application where they give us right here, there's our element right there with our loading right there. We got our shear and our normals right there, and we say now our sigma 1 is given to us as 80 KSI. So we can see right here on our sigma axis, there's 80 KSI right there. Now our sigma 3 is given to us as 0 KSI. So there's our sigma 3 right there. At the center right there, 0 KSI. And our sigma 2 is at negative 40 KSI down here. So now what we can do is we can draw our larger circle around the outside of this right there that we see right there, and that goes from that value right here. If we go from a negative 40 KSI up to an 80 KSI, that's going to be a distance right here, a diameter of this of 120 KSI. So our radius would be half that, or 60 KSI, and that would be our distance as we come up here to our location right here for our max tau, our max shear stress right there. So half of 120 right there, our radius is a tau max of 60 right there that we can get right from our Moore circle. So oftentimes, especially in tension testing right here, we want to know, will the material fail? So we can see we have a failure right here from a dog bone specimen that isn't purely in tension right there. So we have our graphs right here. We have our information dealing with our shear stress and our normal stress. So we can ask ourselves the question, if we're outside of that range of our maximum allowable or maximum shear stress and our maximum normal stress right there, if we're outside of that, it's greater than that, then we're going to expect to see failures. That's something that we want to consider as we're going through and drawing these out right there. We're looking through again, there's our sigma axis right there, there's our tau axis right here. We can see our maximum tau right here. Our tau max is going to be equal to 60 degrees right here. We go back over to our initial diagram there that we looked at right there. We can see our max right here, our T max was 50 right there. So this is something we want to pay attention to. Is it greater than our maximum shear stress? Is it greater than our maximum normal stress right there? And those are predictions of failure. So now we want to take a look again at a real application right here. And in particular, let's take a look at compression right here. We want to ask ourselves, will the material fail? Again, we can look at our Moore circle right there. We can look at our tau max. We can look at our sigma max there, make predictions right there. This is information that we can get either from an actual tension test, some of the manufacturer's data for this stuff, the material properties of this stuff here. We can get some of those sigma values and our tau values from that there, or from testing and we get those actual values for those. Take a look at that, and Moore circles predict if there's going to be failure. So now if we take a look at type of failure right here, let's take a look at a compression failure in a concrete core sample right here. Now we can gain a lot of information from this here, so then we can still get our raw data for this here. We have our force over our displacement right there, and looking at each of those right there, we can redraw our stress strain curve right there, get our modulus elasticity and all that information. Take a look at the curve. Is it brittle? Is it ductile? All that information we can get right here just from that raw test right here for a compression test right here on this column right here. And we have information from this here. We know at the beginning, we know the diameter of this core sample that we took right here of the concrete right there. And this is a prime example of we might not be able to look this up, especially for different types of mixes. We might want to get information from these compression tests to draw out our material properties information for this particular mix right here. This is also something where maybe we're looking at a bridge deck, and this is a lot of work that I've done in the past. We're looking at bridge decks and we're seeing a lot of delaminations, we're seeing a lot of spalling, we're seeing a lot of potentially potholes coming up to the surface right there. So we want to see, is this something with the concrete itself? And one of the questions that, particularly in my research that I've dealt with here, is the porosity of the concrete right there. And we can get some information from that from these core samples and doing some of these compression tests as well. And the issue is, especially up here in the Northeast where they may be using brine and salt, that could leak down through. The more porous the concrete mix, the more that can leak down, get to the rebar and cause corrosion. When the corrosion occurs, then all of a sudden there's a little bit of expansion, which causes a small micro crack around that in the concrete. And then as more of the water comes down in there, it fills it up and then it freezes and expands. So then you get that freeze thaw going expansion within that small crack from the corrosion on the rebar right there, and it gets worse and worse and propagates more and more. The rebar gets more corroded, the cracks get bigger, and then that turns into a delamination at that level right there, and then that propagates up to the surface, and then we start seeing those potholes. So just a real application right there of why we may want to take a look and do some compression testing. So we can go into that bridge deck right there and we can drill out these core samples and we can take a look at that. We can run these tests on there. We can back out our information, find out maybe there's a better mix. Maybe there's a better concrete that we could use. The more information we gather, the more data we collect from this right here, the more we can categorize these. So this is a real application right here, speaking of material failure right there. And this is a case right there where it's not necessarily compression or tension right there, and we can actually get that information from some of these tests right here. And we've seen some ways that we've done tension testing on concrete where we've actually put a rebar into this and then pulled on either end right there. So we want to see how it reacts in both compression and tension right here. Now, the other thing that we can look at here is how it fails. So when we're looking at compression, as you can see here in these two different diagrams, how is this failing? Is it failing just along like this, or is it shearing off like we're seeing over here right there? And from this information for how the failure is occurring in compression right there, we can gather some more information that could be valuable for our design, in this case here, of a concrete bridge deck. So continuing on with our failure theory here, if we want to predict failure, if it's going to occur, one thing that we can do is we can compare the results for failure or yield in a tensile test to the state of stress right there. So that's why it's important to take these tensile tests right there and we compare that to the state of stress right there. From that, we can determine the likelihood of failure or the yield in the element to be designed right there. So this is something we could do actually developing it, and in our prototyping right here as we're making out these samples, test and compare from the tensile test right there and go ahead with our design process from there to tweak it to meet the correct specifications. Now we can go back and show this graphically on an axis of principal stress right here. And sometimes this is useful to get a visual of this to actually look and say, oh yes, we are within this, no we're not within this right there. So going back to material behaviors right here with failure theory, what material behaviors are going to require this right here? Well, we can take a look at normal versus shear strength, and we can also take a look at compressive versus tensile strength. And as I mentioned right there, even with that core sample in our concrete decks, sometimes we want to look at both of those because you have both compression and tension going on. Think about a bridge deck, the way it's loading in three-point bending. Sometimes it's in compression, sometimes it's in tension. Go back to even some of our previous courses right there where we talked about that with three-point bending. If you look at a beam in three-point bending right there, if it's going down like this in the center, all of a sudden the bottom of that beam is going to be in tension and the top of that is going to be in compression. The same applies for a bridge deck right there, where you're going to have certain portions of it in compression, certain portions in tension, and it could be cyclic loading as cars are driving over that, and it could be going back and forth, putting the top in compression and tension and the bottom in compression and tension as well. So that's something that is interesting to see right there, is comparing the compression versus tension results. So now let's take a look here at our maximum normal stress theory. So what here we're going to do is we're going to perform two different tests. We're going to perform a tensile test and a compression test as well. So for each of these, we're going to define an ultimate tensile and an ultimate compressive strength right here. And we're going to represent that graphically. So over here, we can represent that right here. Here is our uniaxial compression and our uniaxial tension test right there. So here is our S sub UC, our ultimate compressive strength, and S sub UT, our ultimate tensile strength right there. So now we can see this is our sigma axis right here. There's our tau axis right here for normal stress down here and our shear stress right up there. So now what we can see from this representation here, so we have both those informations showing those ultimate strengths for compression and tension as a visual representation on our Mohr circle right here. So our principal Mohr circle must lie within these bounds to avoid failure. So these bounds are on either side. So I put these two right next to each other like this right here for tension and compression. So in order to avoid failure, it needs to rely on these bounds right here. So let's do that here. We'll do our first one right here. And we can see that this does lie within those two bounds right there. So we don't have to necessarily say there is going to be failure for that one now. But now if we do this one here, this does not lie. You can see this edge of this right here does not lie within those bounds right there. It goes on the outside of those bounds right there. So therefore, that's potential for failure right there. And this is a good graphical, easy way to represent this using Mohr's circle. So going back to our maximum normal stress theory right here, let's plot this on a principal stress axis right here. So there's again our ultimate compressive strength, our ultimate tensive strength right there. Then we can see now we have sigma 2 up here right here. Now our ultimate tension and ultimate compressive strength right there. And this is for a biaxial stresses. So for example here, our sigma 3 is equal to 0 and sigma 1 and sigma 2 must plot within this area to avoid failure. So we need to make sure that sigma 1 and sigma 2 plot within this to avoid failure right there. So for our application and loading conditions, we can plot a point on this figure right here. So we can use this as another way to visualize this and represent it to determine if we're going to have a failure. So we can see right here, inside the box right here, as long as we're within this right here, there's no failure. But if we're outside of the box, then there is failure, and that's where, again, we want to go back and redesign. So this is why I like this here. It's a quick visual graphical representation that we can utilize, again, using maximum normal stress theory right here to determine, maybe I need to redesign it. And a redesign could be dimensions, could be material, could be loading, all those type of things that we talked about in the design process right there. But if we're outside this right here, it's a way that we can quickly see, yeah, we're outside of this box right here. There's probably going to be a failure going to occur, so we need to go back and do a redesign. So the maximum normal stress theory is also referred to as here called our maximum principal stress theory, which makes sense from what we're looking at from our graph over here. And it's also referred to as our Rankine criterion as well. So these are two other terms you may hear referring back to our maximum normal stress theory that we just discussed. So continuing on with our maximum normal stress theory, let's take a look here for 3 dimensions right here. So we have this cube representation over here. We have our ultimate or our yield strength surfaces right there. So we have our sigma 1 plus and minus y, sigma 2 plus and minus y, and our sigma 3 plus and minus y. And how those relate back to this cube over here is you can see this bottom surface right here is represented by sigma 2 is equal to negative y right there. So this is our sigma 2 axis right here, and we can see this is down here, that bottom surface right there of this right here of a negative y right there. Whereas we have up top here in our sigma 2 axis, there's our top surface right here, which is our sigma 2 of a positive y. Now the same thing for sigma 1. If this is our sigma 1 axis, we have this surface over here, which is our sigma 1 is positive y, but then we have this surface over here, which is our sigma 1 of negative y. Then we can take a look at our third axis right here, our sigma sub 3 right here. So here's our front surface right here for sigma 3 on our cube right there, and that's our sigma 3 is equal to y. Then we have our back surface right over here, which is then going to be that back surface is sigma 3 is equal to a negative y. So now we've been discussing doing some of these different testing here, compression testing, tension testing on different samples right here. So now let's take a look at some of these actual testing machines that can be used. So this right here, we can see a uniaxial testing machine right here in this picture right there. So you can see uniaxial right there. You just have this one actuator right there going in this direction right there. So this would be a uniaxial testing machine, and this is typically what we're going to use for a lot of our compression and tension tests right there, something like that. You have this thing, this could be a lead screw, this could be hydraulic, this could be pneumatic. There's different ways that they can control these right there, and you can see you have your whole control system and your data acquisition system as well going into this system here. We have several of these in Votis, and I'll get into some of that in a minute right here for the different types of tension testing machines, even different uniaxial tension testing machines, again, as we talk about hydraulic versus a lead screw type of machine. So another type, though, is our multi-axis testing machine. So this right here shows a biaxial tension testing machine right here. So you can see right in the center there, there's our sample. So let's just say we want to pull something in 2 different directions like this right here, all in tension right there. This is a great machine to do this. Now, these are not as common. A lot of places don't have these. These are often specially designed for certain applications where you need to do this. It is a great machine to have for a very specific type of application. Now, something like this might not be the best or the optimal, simplest machine to do a simple dog bone tension testing in, but it would still allow it. You could change it programs to just using 2 of those axes and go back to a uniaxial testing machine there. But for the cost and the amount of development to go into one of these, you really most of the times want to use these for a very specific application of testing a certain part that maybe you're developing. Other than that, being a factory that actually develops that part, needing to do quality control testing of that right there throughout the entire production process right there, the only other times you'll really see these types of really specific specialized machines is in testing laboratories. A lot of the government facilities will have some of these where they need to send certain parts in to get spec'd out to meet the standards. And last, a very unique and special case right here, we have a multi-axis material testing machine right here. This is a triaxial one right here. And again, a lot of these are very, very custom designed. I was working with a company testing ratcheting medical tourniquets, and this is something that we needed to really do, was we needed an expansion and 360 degrees around to simulate a limb right there to put it in tension all the way around the whole thing. So a uniaxial machine was just going to push it in one spot. We needed to expand all the way out. So we worked with a couple of these different companies to come up with a special multi-axial testing machine that would expand out in 360 degrees. So again, these are very, very specific and awesome custom design and built. But there are companies out there, even some of the bigger names, that will either custom make one from scratch, or they can have attachments and modifications and add-ons to some of their existing basic tension testing machines or material testing machines that you can expand it into multi-dimension. So speaking of the machines that I've used and that we had in the Voti building on UVM campus right here, this was a 20,000-pound material testing machine. This was a hydraulic machine right here. And this was great for cyclic loading. So I actually, back in the 90s, used this machine for my senior thesis with Burton Snowboards and built a three-point bending machine. And you can actually see part of my rig over there from one of my old tests in the background there. When we put the snowboards in 3-point bending to simulate riding scenario, we wanted to test the cores. We were comparing different types of cores for the Burton snowboards, and we wanted to put this in cyclic loading to simulate X number of days, do life cycle testing of this, of X number of hours of riding, X days of riding, to see when the fibers in the core right there were going to break down and snap, and you'd lose some of the camber. So we wanted to use cyclic loading. So this is a great machine. Even though it's a uniaxial machine, the fact that it was capable of doing cyclic loading, and we could simulate that cyclic loading to what someone would see in a typical day of riding, that was very, very useful. So this was a great machine for life cycle testing. We could literally set it, program it, say just then do this many cycles at this rate, at this stroke right there, leave it. It's going to require the data, whatever data acquisition rate we programmed in there, walk away, come back, and then take a look at the data and see, did it meet our criteria? How long did it last? All that type of information. So this was another type of, now we're talking about different types. We said lead screw versus hydraulic. This is a lead screw machine. You can see these 4 lead screws right there. Now this definitely goes a lot higher load rate. This is up to 60,000 pound right there in this Tenney-Solson system, but you can see this is ancient. We would actually use this one for some of our tension testing of dog bone specimens that we could put in between these two things. We had an attachment there, an attachment there, and this platform right here would move up and down on those lead screws right there, and we put our dog bone specimen right in the center of those two right there, and slowly pull on it. Now the great thing about this machine though too was we could also use this for compression testing. So we looked at some of those core samples of concrete right there. We could put them down here, put our core sample in something like this right there, and then bring this down, lower it down, and apply compression to that sample right there, and we'd have to read the load off of this guy right there. Eventually we did hook up a computer and a new system right there, and we're able to actually get out some of the force versus displacement data. It actually did allow us to program in some of the dimensions and actually get some stress strain data right from the program for that as well, even for this really old Tenney-Solson machine right there. But the downside of using one of these lead screw machines right there is the cyclic loading, not so much. This is more of a static type of loading machine right there. It's a very slow rate that we're going to move this on. It's not going back up and down like the hydraulic machine we use for the cyclic cycling back in the back there, which you can see there's the MTS machine back in the corner hidden there. That was the hydraulic machine that we could use for that cyclic loading and do some of that life cycle testing. Another smaller desktop version, which is great for if we're really looking at some of the finer details, we want to see differences of a couple pounds. Maybe that 60,000 pound machine is only going to be accurate to 10 or 20 pounds plus or minus. Whereas this one right here, we get down to sub 1 pound accuracy with this right here. And we could, again, this is a lead screw in here, so it's another lead screw uniaxial machine right there that we had. This is great. It only goes up to 1,000 pounds, so it's for the lower loads, but with more accurate results right there. We also were able to use this one with an extensometer to really get some accurate results right there for displacement as well as our load right there. So this is another great machine. This one, even though it wasn't great for quick cyclic loading, we still could program it to load and unload and load and unload and do some life cycle testing on this one as well. So this was a great little machine for the lower loads and a little bit higher accuracy. And we can see we also had grips in the background here that we could do some dog bone specimen samples testing as well for tension tests. So utilizing some of these machines for different applications. So we talked about the difference between these multi-axis, uniaxial machines right there. Well, what if we wanted a case like this? So I had been contracted by a local company that does granite countertops, and they wanted to take a look at the maximum amount of overhang that they could have on this if the person were to lean on the counter before it broke. So it was a very interesting test. So this was the setup that I had for them and how I planned to utilize this right here. So what we thought of doing was coming over with this tension testing machine right there, and then we could vary this and just show, okay, if we vary this length right here, and this is a simple calculation, we could also do an analytical hand calculation right there for this type of granite right here, but we're really looking at the different types of granite as well as the overhang. So this is a great design project right here if anybody's interested in partnering with this company. Couple questions we could ask ourselves for the design criteria for this. What type of material, what type of granite could we use, the maximum amount of overhang, the maximum load that could hold right there, as well as the thickness of the granite as well right there. So all of those can go into play right there for this right here we're seeing. Now, the thing to think about with this is, yeah, we could say a person weighs, no more than, we'll say like 250 pounds for the average person right there, average adult. but we'll put in a safety factor of it as well. So maybe we'll go up to 500 or 600 pounds right there with a safety factor in that right there. But this is considering static loading. What if somebody jumps on the edge of the counter? And you got that impact loading right there. So all of those type of things, that might be a little bit more FEA that you'd want to do on something like this. So even a simple project like this right here, where you can specify the type of material, you can specify the dimension of the overhang, and you can specify the thickness of the granite right there, and then figure out, okay, well, if for my criteria right here, I need to go up to 1,000 pounds of static loading right there, will it handle it with those criteria? And then again, that iterative design process right there, keep testing it. Well, no, 5 inches overhang was too much, or ½ inch was too thin right there, or this material definitely didn't work right there. Let's try a different material for that right there. This is interesting. Now, the testing procedure for this also became very interesting in the fact that this needed to be actually fixed down to this lab bench right there and find a way to bolt this down in spot right there, so that other than that, it could just lift this whole machine right up when we push down with the actuator right there on this. So that's another thing we needed to consider when we were doing this as well. So continuing on looking at our maximum normal stress criteria right here, what I want to take a look at now is the kind of definition and what this actually is. So the maximum stress criteria, also known as normal stress right here, Coulomb or Rankine criteria. This is often used to predict the failure of brittle materials. So that's what we're going to utilize this for, is predicting that failure of brittle materials. So the maximum stress criteria states that the failure occurs when the maximum or normal principal stress right there reaches either the uniaxial tension strength, or sigma sub t, or the uniaxial compression, sigma sub c right there. So as far as an equation goes, this says that our negative sigma c is less than our sigma 1 comma sigma 2, which is less than our sigma t, where sigma 1 and sigma 2 are the principal stresses for 2D stress. Now graphically, we can represent this here. The maximum stress criteria requires that 2 principal stresses lie within the green zone predicted below. So again, if 2 of these lie within this here, we're good. If they don't, then it does not necessarily follow the criterion. So now going back to our graphical representation right here, we can see what we have in this graph here is uniaxial tension right there. So we're just looking at tension. So our S sub yt is our yield strength and tension right there. So we can draw that out on our axis right here. There's our sigma axis. There's our shear axis right there. Now this distance going right here, which is the diameter of that circle right there, this is the principle. This is the fact that our principal Mohr circle must rely within these bounds to avoid failure right there. So these are the 2 bounds right here that our Mohr circle, our principal Mohr circle, must lie within to avoid failure. So let's just take a look. If we have this right here, we can see now for this example right here that this does not lie within these bounds, so therefore does not necessarily avoid failure. So let's take a look now at Mohr's theory and go into a little bit of detail and review of that there. So Mohr's theory suggests that failure occurs when Mohr's circle at a point in the body exceeds the envelope created by the 2 Mohr circles for our uniaxial tensile strength right here in red, and our uniaxial compression strength right here in blue right there. So in the graph below, we can see the envelope shown in this figure right there. So we can see over here, we have our uniaxial tensile strength right here, our sigma sub t with this red circle right there, uniaxial tension. Then we have over here uniaxial compression with our blue circle right there, our sigma sub c right there like that. So now this left blue circle is for the uniaxial compression at the limiting compression stress right here of our sigma c of that material. Likewise, the right circle in red right here is for uniaxial tension at the limiting tension stress right here, our sigma sub t that we see right there. Now the middle circle on the figure right here, this dashed line, this black dashed line, this represents the maximum allowable stress for an intermediate stress state right there. So all intermediate stress states fall into one of 4 different categories, which I'm going to show in the following table right here. So each case defines the maximum allowable values for the 2 principal stresses to avoid failure. So that's something that's important. We're trying to figure out how we can avoid failure. That's going to help us determine that right there. So you can see then again, there's our blue circle, uniaxial compression, red circle, uniaxial tension right there. And now we can see this center right here for our intermediate stress right here, this black dash circle right there. And you see this one right here fits within that envelope. Now, as we mentioned, all these immediate stress states fall into one of the following 4 categories on this table below here. Now, each of these 4 cases defines the maximum allowable value of the 2 principal stresses in order for us to avoid that failure right there. So in case 1, both of them are in tension, so our sigma 1 is greater than 0 and our sigma 2 is greater than 0. So in this case here, our sigma 1 is less than our sigma sub t, and our sigma 2 is less than our sigma sub t as well. Now, for our case number 2, both of these are in compression right here. So for compression right here, our sigma 1 is less than 0 and our sigma 2 is less than 0 because it's compression right there. And sigma 1 is going to be greater than our negative sigma sub c, and sigma sub 2 is also going to be greater than our negative sigma sub c right there for compression. Now, for case 3, we have sigma 1 is in tension and sigma 2 is in compression, so sigma 1 is greater than 0, sigma 2 is less than 0. And we have this relationship here that sigma 1 over delta t plus sigma 2 over delta negative c is going to be less than 0. Then we have the reverse case of that where sigma 1 is in compression, sigma 2 is in tension, so sigma 1 is less than 0, sigma 2 is greater than 0, and our sigma 1 over negative c plus sigma 2 over sigma t is going to be less than 1. So what I want to do next is go through my hand solution to a simple problem from our textbook right here. Where this problem here, we have a large rectangular sheet with a 1-inch long central crack. This fractures when loaded to 80 KSI. So we can see this in the diagram down below right here. And this sheet now contains a similar crack of 1.75 inches. For that, they want us to determine the fracture load or our stress for the similar sheet. So this is the first example problem we're going to go through today. We have a large rectangular sheet. Keyword here being this is a large rectangular sheet here. They tell us that there is a long central crack fracture when it's loaded to a known load of 80 KSI. They give us the dimensions of this long crack, and they also tell us that there's a similar sheet containing a 1.75 inch crack as well. So shown down here we have our given schematic and diagram. We can see, okay, the width of this sheet is 2W. Central crack we have here is 2C. We have a thickness of T, and here is this external load P over here. They want us to find the fracture load or the stress for the similar sheet, which again up here the similar sheet has that 1.75 inch crack there. So we come down here, and the first thing we really want to do is from this given information go through, write everything out in terms of variables and units and how it relates to our given schematic diagram over here. So again, we have all of these different variables here with what they relate to as far as physical features on this given schematic. So once we have this, we've taken a look at the exact example problem. First thing we want to do is very similar to like we've gone through every other problem before, is to actually write this out in the correct format. So that's what we're going to do next. Remove this guy here, and now we'll go through this example problem and write down all of our givens, what they're looking for us to solve for, and redraw our diagram out in a little bit more detail. So for this guy here, a couple things are given within the problem statement. We know it's a large rectangular sheet. It's 1 inch long and contains a central crack. It fractures when loaded to a known load, and there's going to be two similar sheets that we're looking at here. So if we write down all the other information from the given schematic over to the right over here, so we have the 80 KSI, 2W is a large sheet, T is a thin sheet, 2C is equal to 1 inch. Redraw this out, kind of color coordinated a little bit here, so we have this external load in blue, P up here, our thickness in red over here, T, crack in orange here of 2C, length over here, the dimension in red here, 2W. And again, they want us to find this fracture load or the stress for the similar sheet. Now, one of the main things we want to do with this is to come up with some general assumptions, and these will be very similar for all these types of problems, and I do plan to give a problem similar to this as a homework problem. So this is going to be something to take note of here, and we take a look at these assumptions. So with these assumptions here, the first assumption you want to make is that the crack length is a small fraction of the plate width. And this goes back to how they've called this a large plate in the beginning in the problem statement. Next assumption, tensile stress based on the net area, so minus the area of the actual crack. So we'll see this in some of the equations in later problems as well. And this is going to be less than the yield strength. So with this assumption, this is something that we're going to want to double check at the end of these problems. Yielding has occurred within one small volume of the material at the crack root, and then the last assumption we're going to make is that crack propagation to the total fracture occurs instantaneously when the limiting value of the stress intensity factor Ki equals or exceeds the fracture toughness of KIC for the material. So those are the assumptions that we're going to make when setting up this problem. The next step in this is to go through all of the givens and what we're looking for and determine what our key equation is going to be and how to start our solution for this problem. So as we start the solution to this problem here, what we want to do, taking some of these assumptions into account, so for a large rectangular sheet, we have no geometric effects. So Ki is equal to KIC, and where this comes into play is equation 6.1 and 6.12 in our textbook. So we have this assumption here. So we know that these two guys are equal. So the next step in our solution is we take a look at some of the given geometries of the diagram. So we know that 2c is equal to 1 inch. So if 2c is equal to 1 inch, then our c value is equal to half of an inch. We also have our value here of KSI, which is given to us in the problem statement. So then we can jump right to those two equations I just mentioned, and 6.1 and 6.2, look through that, and these are given on page 165 of your textbook. So we start off that K sub I is equal to our sigma times the square root of pi c. We can rearrange that slightly, and we can see the simplification of this as it leads into equation 6.2, and we have 1.8 times the square root of c times our value here of our sigma g, which we're given up above in the problem statement. And we can go through these here and start plugging in our known values. We've just solved for c. So again, if 2c was 1 inch, c is a half inch, we can plug that right in there under our square root, and we have our sigma value here of 80 ksi. So we can then plug these in. We know that ki is equal to kic, which is equal to now 101.82 ksi times the square root of inches. So this is the units we're going to be looking for these guys here.